Good afternoon, calculus class. Today we are going to cover section 3.7 in your textbook. There's quite a bit in section 3.7. It's derivatives and inverse functions. And then in particular, as one example for inverse functions that we will need as calculus students, we're going to look at differentiation and derivatives with inverse trig functions. So that's what's on the agenda for today. And then on Wednesday, we'll look at another example of inverse functions as we look at exponential and logarithm functions, and we'll talk about the derivatives of those two types of functions on Wednesday. And that will finish up everything we've got out of Chapter 3. We've done, remember, Section 4.1 on related rates already last week, and so next Monday we'll start in a big way in Chapter 4 and looking at applications of differentiation. A couple of things of note for you guys. We'll have online office hours this week, Monday, Tuesday, and Wednesday from 8 to 9 each evening, and Thursday from 1 to 2. So stop by during online office hours if you have questions about something that we've covered in the lecture. The status of Exam 1. So I've got all the Exam 1s mostly last Wednesday. I got them mostly turned into me. So I'm in the process of grading those as we speak. And so my goal is to try to have those finished by Wednesday or Thursday of this week. I will post those on your D2L gradebook, just like I did homework 1. And so you can go to the D2L gradebook and find your Exam 1 grade there. Hopefully by Thursday those will be posted. I will send an email to everyone when I have posted those grades. If you want a graded copy of your exam emailed back to you, then please email me. We'll wait until I send an email out that I've posted the grades. But after I've posted that email later in the week, if you want a copy of your graded exam, please go ahead and email me, and then I will respond to your email with an attachment that is your graded exam. So be looking for that. Homework 3 is due at the end of next week. That covers sections 3.8, 3.9, and 4.1. So be looking at that for sure. 4.1 in particular, I want to point out, is on related rates, and so that gives students some trouble sometimes. And section 3.8 is on implicit differentiation. That also gives students some trouble. So make sure you give yourself plenty of time. Do not be working on that at the very last second. And let's try to see if we can keep up with the homework. Some of you are frantically cramming your homework into the last day or two before it's due, and that's really not doing you any good to prepare for the next exam. You need to keep up with the homework on a daily basis. You need to be looking at the textbook homework, not just the homework that's to turn in, but the textbook homework also. And so, I think some of you are cramming too much work into the very end just before the exam, and then you're frantically trying to prepare for the test. So, see if you can put your effort in on a little bit more consistent daily basis during the semester. That would be a big benefit to you as you go through the rest of the class. All right, so today we're going to be talking about inverse functions. And so the first thing I'm going to do is I'm going to talk a little bit just about inverse functions and the algebra with inverse functions. I certainly have expected that you have all seen and talked about inverse functions several times in your mathematical careers, whether it be in an algebra class in high school or pre-calculus, someplace like that. But I want to kind of go back over the highlights of inverse functions a little bit and make sure that you kind of refresh your memory on what it means for two functions to be inverses. That is important if you're going to talk about inverse trig functions. If you're going to talk about exponential and logarithm functions in calculus, you need to understand some things and recall some things about functions that are inverses. So first of all, recall that if f of a is equal to b. If we have some function f and it takes a to b, then its inverse function, if f is, it got an inverse, then the inverse function, and that's the notation for the inverse, remember, is f with what looks like a -1 as an exponent, but remember that -1 is not an exponent, that f inverse of b is equal to a. So notice that if two functions are inverses of each other, then what do? They switch or interchange x and y values. Right, so the graph of f contains the point AB, and the graph of f inverse contains the point BA, right, that they interchange x and y values. And because they interchange x and y values, what the implication there is then that is the domain of f the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. Right, so they interchange domains and ranges. And in terms of asymptotes, don't forget that the implication there then is that if f, let's see, so if f has a vertical asymptote, at x equals a, then f inverse has a horizontal asymptote at y equals a. So remember, they kind of switch asymptotes. Also, don't forget that not all functions have inverses. Not all functions have inverses that are functions. And we only want to talk about, when we're talking about inverse functions, we're only talking about functions whose inverses actually are functions. So not all functions have inverses that are functions. And remember how that works is that functions, if f is 1-to-1, if f is 1-to-1, so in other words, it passes the horizontal line test, then f inverse is a function. Right, and if f is not 1-to-1, then its inverse is not a function. So if f is not 1-to-1, in other words, its graph fails the horizontal line test, then the inverse of f is not a function. All right, so as we go through this, we're only talking about functions whose inverses are actually functions themselves. In other words, the only functions we will be talking about are functions that are 1-to-1, that their graphs pass the horizontal line test. All right, so let's look at a function here, let's not look at a function. Let's just, first of all, just look at a point. If you've got this point right here, and we'll call that point AB, and let's say that AB is on the graph of f. On the graph of f, then when we switch that point around, so that would be the point BA, which would be like approximately right there. Trying to estimate it a little bit. But those two points are mirror images of each other around this line y equals x right here. And if you connect those 2 points, in fact, the line y equals x bisects it, and it's perpendicular like that. That idea implies then that f and f inverse have graphs that are reflections around y equals x. In other words, that they're symmetric around the line y equals x. All right, so what we're going to do is we're going to look at a function. I'm going to look at an example here. Let's say we have this function f of x equals x cubed minus 1. So x cubed minus 1, if we look at the graph of that function, so x cubed minus 1 is the cube function shifted down 1 unit. And so here's our cube function. It looks something like this. All right, and so notice that that function is 1-to-1. So this function is 1-to-1. Its inverse is a function. Now, to graph the inverse of this function, you could just interchange x and y values and sketch the new graph, or you could actually create the inverse function algebraically and then graph it that way. So now if you just interchange these values, going point by point from left to right there that I've got plotted there, you've got the point -2, -1, -2 would become the point -2, -1. 0, -1 would be -1, 0, and then 1, 0 would be 0, 1. And so these points right here would be all on the inverse graph. We also know that the inverse graph has to be a reflection of the cube graph around the line y equals x, like that. And so, that would help you make a sketch of the graph, and you'd get a sketch that looks something like this. Right? And so the red graph is the graph of our function f, and then the kind of pinkish graph there would be the graph of f inverse. And notice that they're reflections around the line y equals x. Also notice that that graph, f inverse, should look familiar to you. That's just the cube root graph shifted to the left 1 unit, and we can show that by actually finding the inverse algebraically. So if we find f inverse algebraically, what we do is we switch x and y values, because that's what inverses do. So this would become x equals y cubed minus 1. So we switch x and y. And then we solve for y. So to solve this equation for y, we would add 1 to both sides, and then we take the cube root of both sides, and sure enough, we get the cube root function shifted to the left 1 unit, and there's our inverse right there. So a lot going on here. You need to know that a function and its inverse have graphs that are reflections around the line y equals x. And you also need to know how to find an inverse by interchanging the x and y values and then solving for y. All right, notice that both graphs do pass the horizontal line test, so that they are both 1-to-1 functions, and so that means their inverses are going to be functions. All right, so now if we go on here and we look at this function, let's say we look at f of x equals x squared. Notice that that function, that graph is a parabola, vertex at the origin. And notice that that graph fails the horizontal line test. This one fails the horizontal line test. And so this function is not 1-to-1, and so its inverse is not a function. right? Remember, that means that the inverse fails the vertical line test. And if you switched x and y and look at the graph that was the mirror image around y equals x, you would actually get this graph right here. And so notice you can see that that graph is clearly, that's the graph of the inverse, and it's not a function right there. And so what we do in a case like this is we take the function, so in this case f of x equals x squared, and we actually restrict the domain to so that the piece, and this is if we can actually do this. So it's not necessarily the case that we can do this, but if we can, we try to. In this case, the square function, we can restrict the domain. So for example, x greater than or equal to 0, and we're left with just that piece right there. And that piece, so that's the restricted square function, that piece does, in fact, pass the horizontal line test. And because it passes the horizontal line test, this function is one-to-one, and its inverse is a function. Right, and in fact, the inverse of this graph, right, if we look like that, or drew the graph that was the mirror image like that, we get that particular graph, and you can see that that's f inverse right there, and this is the graph of f right here. And so you can say that f inverse clearly is a function in this case. All right, so now what we want to do is we want to talk about a little bit about derivatives with functions that are inverses of each other. So if we talk or look at our function f of x equals x cubed minus 1 that we had on the screen on the last page, f of x equals x cubed minus 1. So that's the cube function shifted down 1 unit. Right, we had this sketched on the previous screen. And so that graph, we know, kind of looks like this. This is our cube function, shifted down 1 unit. And we have a graph like this. So there's our graph of f, like that. And then our graph of f inverse, which we had on the screen a minute ago. So it goes through those 3 points, and this graph looks like this. So what we want to do is look at mirror image points on a graph like this and talk about how their derivatives relate to each other. In other words, how the slopes of the tangent lines relate to each other at mirror image points. So let's look at, we're going to look at these 2 points right here on the cube function shifted downward and the cube root function shifted to the left. And what we're interested in looking at are the slopes of the tangent lines at those 2 points. So let's look at slopes of tangent lines at points that are mirror images. And so the point I picked was this point right here at 1, 0, and this point right here at 0, 1. Right? Those are mirror images of each other for these 2 functions that are inverses of each other. All right, so if we want to look at the derivative of x cubed minus 1, that's easy. That's just 3x squared. And then we evaluate that at 1, because it's the point 1, 0 on that function that we're interested in. Then f prime of 1 is equal to 3. And so that's the slope of the tangent at that point is 3. Now let's look at the inverse function. Now the inverse function, and we created that function on the previous screen, the inverse function, f inverse, was the cube root of x plus 1. And so what we want to do is find the what the value of that derivative is at the point 0, 1. So let's see. So f inverse of x prime, so we're taking the derivative of that function. That would be a chain rule problem. and that would be 1/3 times x plus 1 to the negative 2/3. That would be the derivative of the outside using the power rule. And the derivative of the inside would just be 1. So f inverse of x prime would be 1/3 times x plus 1 to the 2/3. And then what do we want to do there? We want to evaluate that at, in particular, the point at the x value 0. Right? So we were trying to evaluate that at 0. So f inverse at 0, the derivative of that function, evaluated at 0, notice would just be 1/3, right? Because all we're doing is substituting 0 in to this function right here. And so notice what happens, and this is not a coincidence, is that the derivatives of mirror image points are reciprocals of each other. Right? That's what we want to try to get across here. Is that, and that's not a coincidence, that's always going to be true, is that they're reciprocals of each other. So if, in general then, what we have, if f and g are inverses of each other, so first of all, that tells us that f of a is equal to b, and that AB is on the graph of F. And we also know that G of B is equal to A, that BA is on the graph of G. That what's going to happen here is that f prime of A and G prime at B are reciprocals. In other words, you might see it written this way, that f prime of A is equal to 1/G prime of B, like that. But that's the main idea here that I'm trying to get across, is that they're actually reciprocals of each other when you're looking at mirror image points. If you look in the textbook, the author has it written basically the same way, but kind of like this, that, let's see, so they have it written that g of x if g of x is the g prime of x is equal to 1/f prime of g of x. That's the way the textbook has it written out. But anyway, I would much rather you just kind of know what it means in words, basically not necessarily in symbols, but what it means in words. So we're going to be on page 309. We're going to look at an example or two to kind of talk about this. I'm not going to make a huge big deal about this, but I would like you to know the basics behind this. So this is on page 309 of your book, section 3.7. And we're looking at problem number 264. Problem number 264, you're given a function f of x equals 6x minus 1, and the x value is x equals -2. And the directions are, use the functions y equals f of x to find the derivative at x equals a, and then the inverse function, and then find the derivative of the inverse at f of a. Okay, so this is easy because this is a linear function. So f prime of x is simply just 6, and so f prime at -2 is going to be 6. No big deal. All right, now if you evaluate the function f at -2, you get -13. All right, so keep that in mind. So now let's generate the inverse of this function. Now find f inverse. Okay, so we know how to do that. To find f inverse, we switch x and y. So you have x equals 6y minus 1. You solve for y, you have x plus 1 equals 6y. And then you divide by 6 and you get, or multiply by 1/6, and you get 1/6 x plus 1/6 equals y. That's the way I'm going to write it. And so f inverse here is equal to 1/6 x plus 1/6. All right, and so what do we know here? That for our function, you know that f of -2 is -13. You also know that f inverse of -13 is equal to -2. You could certainly verify that in the function we just talked about. So now, if we find the derivative of this function, so f inverse prime of x is just 1/6, and f inverse prime, in particular, -13, then, would certainly also be 1/6. And what do you have here? That the derivative at -2, the derivative of f at -2 is 6. The derivative of f inverse at -13 is equal to 1/6. They're reciprocals of each other. And that's what you're trying to show here. All right, let's look at a different problem. Let's look at problem let's look at problem number 266 on the same page. 266, you have f of x equals 9 minus x squared. And the restriction is on x in this case, because it's a square function, it wouldn't be 1-to-1 if you just wrote the function out. But if you use this restriction that x has to be between 0 and 3, then it is a 1-to-1 function. And we're looking at specifically at x equals 2. All right, so what is, let's go ahead and find f of 2 in this problem. F of 2 is equal to 9 minus 4, or 5. All right, so the point we're talking about here on the graph of f is 2, 5. Okay, so so now we're going to try to find f inverse. Well, let's first find f prime. So f prime of x is -2x. And f prime evaluated when x is 2 would be -2 times 2, or -4. And so that -4 is the slope of the tangent on the graph of f at the point 2, 5, right? So this is, we know the point 2, 5 is on the graph of f, and then the slope of the tangent is -4. So that's the slope of the tangent at the point 2, 5. It's -4. All right, now find f inverse. So f inverse in this problem, you have y equals 9 minus x squared. We interchange x and y. You have x equals 9 minus y squared. I'll add y squared and subtract 9. And I'll take the square root. Now, typically when you take the square root, you use plus or minus, but we just use the positive square root here because of the restriction that x has to be between 0 and 3. So if x has to be between 0 and 3, that's telling you that y has got to be restricted also, that y has got to be between 0 and 9. So the restriction, on the original function, you know that y has to be between 0 and 9. That's the restriction that comes along with that one for the function f. Right? If you use x values between 0 and 3, you get y values between 0 and 9, including 0 and 9. And so those restrictions flip around on this problem down here, and we've got that x has to be bounded between 0 and 9, and that would be okay on this function. And then y would have to be bounded between 0 and 3. like so. All right, and so there's our inverse function. So f inverse with the restriction that x is between 0 and 9 is equal to the square root of 9 minus x. All right, so now we find f inverse prime of x. That would be a chain rule problem. And that'd be 1/2 times 9 minus x to the negative 1/2 times negative 1. And so that would give you negative 1 over 2 times the square root of 9 minus x, like that. All right, and so then we take our derivative we just found and we evaluate it at the mirror. Remember, the mirror image point in this case is 5, 2, right? 5, 2 is the point that we want to look at. It's the mirror image of 2, 5. And so 5, 2, you're going to substitute 5 in for x right here, and you get, for our derivative, and you get negative 1 over 2 times the square root of 9 minus 5, and so you get negative 1/4, like that. And what do we get? We got reciprocals, right? That's what we're talking about here. That's what's going on. That's what we wanted to show, is that the slopes of the tangents were reciprocals at mirror image points. All right, so kind of going back through this, we were given a function f. We found its derivative. We were given an x value, so we had a point on the graph of f. The point is 2, 5. It's on the graph of f. So what do we know? That 5, 2 is on the graph of f inverse. Right here, 5, 2 is on the graph of f inverse. And so we find f inverse, we find its derivative, and we evaluate that derivative at 5, and we get the reciprocal of the original slope. Okay, so that's the key idea. That's what I want you to know for derivatives of functions that are inverses. And so now what we're going to do is we're going to turn our attention to today and on Wednesday some functions that are specific examples of inverse functions that are important in calculus. In the first group are the inverse trig functions. And then on Wednesday we'll look at exponential and logarithm functions. So we're looking at inverse trig functions first of all today. Now the trig functions, have some issues with them, associated with them when you're talking about inverses, because the trig functions, none of them are one-to-one. And so if you're going to start off with f of x equals sine x, for example, so that's the one we're going to start with here. That function is clearly, fails the horizontal line test. It's clearly not one-to-one. Right? This function is not one-to-one. It fails the horizontal line test. In fact, it fails it really, really badly, doesn't it? So let's see, if we scale off like this, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and then over here we have negative pi over 2, and so on for our sine graph. And this is definitely not to scale, just so you know. It's not horribly out of scale, but it is definitely not a graph that's sketched to scale here. And we graph the sine function, right? We get this graph. Oscillates, back and forth between -1 and 1. We know that. And you get this graph that's clearly not one-to-one. And I knew there was something wrong there. At this point right here, I kind of put it in the wrong spot. Should have been down here. It's better like that. Okay, now it looks better. Our graph continues on, and it continues on like that. All right, so it's definitely not one-to-one. So what we do is we restrict the domain for this function, and we restrict it to just x values between negative pi over 2 and pi over 2. And so we look at what's called the restricted sine function. Now the restricted sine function, okay, so that's just the piece of that graph that's between negative pi over 2 and pi over 2. So here's negative pi over 2 right here. Here's pi over 2 right here. Here's 1 and negative 1 on the y-axis. And we get just this piece of the graph right here. And this piece is 1 to 1. So this is what we call the restricted sign function. Sometimes you'll see textbooks make a notation change here. But just understand that whenever we're talking about inverses, you are automatically talking about the restricted sign function, not the sign function itself. And so we're not going to use any special notation here. But so that's the domain for this function. Right, there's the domain. The range, notice, is not changed. We purposely pick a domain where the range would still be from negative 1 to 1 for the sign graph. And so this function passes the horizontal line test. And so since it passes the horizontal line test, it is 1 to 1, and its inverse is a function. All right, so we get what we call the inverse sign function. So the inverse sign function, one notation that you'll see for the inverse sign function looks like this, is that it's y equals inverse sine x, like that, where you use a negative 1. It kind of looks like an exponent, and it reminds you of the inverse notation that we use in algebra. Another notation that's used where you don't use that kind of exponent notation at all is the arc notation, and you call it arc sine x. Those notations are interchangeable. Those mean the same thing. They're talking about the same function. Those are both the inverse of the restricted sign function. I will use those notations interchangeably. The textbook will use them interchangeably. But you'll see both notations throughout calculus. In fact, I'll probably use the arc notation more commonly than the other notation. All right, so what's the domain for this function? Well, the domain would be all the x values from negative 1 to 1. Remember, the domains and ranges would have to switch between the sine function and the inverse sine function. And so the domain here would be from negative 1 to 1, and the range would be from negative pi over 2 to pi over 2. And so, if you're thinking about it in terms of quadrant angles, the sine function, the restricted sine function only takes on quadrant 1 and quadrant 4 angles from negative pi over 2 to pi over 2. And those are the x values that it takes in. So the arcsine function, the values that it spits out, would be quadrant 1 and quadrant 4 angles only. All right, so those are the only kinds of answers that you can get for the inverse sine function. All right, so just let's look at some evaluating here for a minute. So let's say, for example, that you have well, first of all, before we even do that, let's write some notation down. If you have y equals arc sine x, then the equivalent statement then would be that sine y equals x, like that. If y is arc sine of x, then sine of y is equal to x. Or another way you could look at this is write out what we call the inverse cancellation property. An inverse cancellation, if you recall from algebra, is that if you take two functions that are inverses of each other and you compose them, right? So f of f inverse of x, you get x, and f inverse of f of x is equal to x. That inverses kind of cancel each other out. It's not really what's happening, but they, if you apply both the inverse function and the original function to an x value, it's like you're not doing anything at all. And so in the case of the sine function, then inverse cancellation would look like this, that the sine, the arc sine of x is equal to x, and the arc sine of the sine of x is equal to x. Don't forget, when we're writing down the sine function in these statements, that this is the restricted sine function, by the way. And so notice you could you could, if you think about that statement or that inverse cancellation for the inverse sine function, then what you have, if you start with y equals arc sine x, and then you apply the sine function to both sides there, you have sine y. Go ahead and try to work out the colors correctly here. So you have the sine of y equals the sine of the arc sine. So notice I am applying the sine function to both sides there. And what do you get? You get sine y is sine y is equal to x, just like we saw above. And the key here is that you just need to know that these two are equivalent statements. All right, that if y is arc sine x, then sine y is equal to x. Okay, so with that in mind, then we could actually go through and do some calculations here to kind of practice stuff about the arc sine of x. So if you have arc sine of 1/2 and you're trying to calculate that value, remember the domain for the arc sine function is everything from -1 to 1, so 1/2 is in that domain, so that's okay to write that out. So arc sine of 1/2 equals what? And we simply write out the equivalent sine statement from above, and what we're really being asked here is the sine of what is equal to 1/2. And we have to remember this is the restricted sine function, so we can only write in values there from -pi/2 to pi/2. And the sine, we know that the sine of pi/6, the sine of pi/6 is equal to 1/2. So since the sine of pi/6 is equal to 1/2, then we can write at the top that arc sine of 1/2 is equal to, in fact, pi/6. Right, like that. Okay, if we had the arc sine of the square root of 2/2, and you're trying to figure out what the arc sine of square root of 2/2 is. Square root of 2/2 is in the correct domain, so that's okay. The domain for the arc sine function, remember, x values from -1 to 1. So if you find the arc sine of the square root of 2/2, or you find the arc sine of the square root of 2/2, then if you write sine of what is equal to the square root of 2/2, then remember you're talking about the restricted sine function here. So you know that the sine of pi/4 is the square root of 2/2. And so that would give us, going back to the original statement then, that would give us that arc sine of square root of 2/2 is equal to pi/4. All right, arc sine of negative square root of 3/2. So you have to be really careful with negatives. You have to pay attention to the restrictions here. If you're not sure what that is, then you would write the equivalent sine statement out, that the sine of what is equal to negative square root of 3/2. But remember, we're talking about the restricted sine function. And so this x value has got to be between -pi/2 and pi/2. Right? And so if you're thinking about what that would have to be, it would have to be a quadrant 4 angle, and it'd have to be a quadrant 4 angle between -pi/2 and 0, and so you end up with -pi/3 right here. The sine of -pi/3 is equal to negative square root of 3/2. Sine of pi/3 is equal to the square root of 3/2, so the sine of -pi/3 is negative square root of 3/2. And so what do we have here? That arc sine of negative square root of 3/2 would be equal to -pi/3. All right, so you need to pay attention. So pay attention to the restrictions. So pay attention to restrictions. Your calculator also obeys these restrictions, just so you know. All right, so now we could go through, so there's our arcsine function. We could go through the exact same process for the cosine and for the tangent and so on. So if you have f of x equals cosine x, just like with the sine function, that graph fails the horizontal line test miserably. Right? You can draw a horizontal line that intersects it in an infinite number of places. So here's one, it's a part of our cosine graph. Graph is clearly not one-to-one. Remember, all this is just a shift of the sine graph. So it's really the same graph as the sine graph, just shifted horizontally. And so not one-to-one. Inverse is not a function. So what do? We restrict the domain on this function, and so that what we have is one-to-one. So we restrict the domain. And the piece that we use in this case, the restriction we use, is from 0 to pi. That's the piece that we keep. Notice it's a different, unfortunately, because the graph's in a different place horizontally, we can't keep the same piece that we keep with the sine graph. And so the restricted cosine graph, just from 0 to pi, is this piece right here. By the way, notice that that's a falling piece right there. And that's our restricted sine function, by the way. Notice it's falling, and so its derivative is going to have to be negative. So this is the restricted cosine graph. Looks like that. And so what's the domain on that? It is from 0 to pi. And the range would be from -1 to 1. So now, with that information, then we can now look at f of x equals arc cosine. And what do we have there? The arc cosine, its domain would be negative, all the x values from -1 to 1, and its range would be values from 0 to pi. In terms of quadrants for angles in standard position, notice that this is quadrant 1 and 2 angles, quadrant 1 and 2 angles for the arc cosine, as opposed to 1 and 4 like the arc sine function. All right, so if you were going to do some of that, and by the way, you still have inverse cancellation for this. You have that if y is the arc cosine of x, that the cosine of y is equal to x. Those would be equivalent statements. Remember, again, that would be the restricted cosine that I just wrote down. And then you have inverse cancellation. So you have the cosine of the arc cosine of x is equal to x. Then you have the arc cosine of the cosine of x is equal to x, like that. All right, and again, if we, let's look at a little bit of evaluating here. The arc cosine of the square root of 3 over 2. Square root of 3 over 2 is in the correct domain for the arc cosine function, and to figure that out, we would say, okay, the cosine of what is equal to the square root of 3 over 2. You have to pay attention to the restriction that this is the restricted cosine function, and so we can only use values from 0 to pi. And so we get the cosine of pi over 6 is equal to the square root of 3 over 2. You remember, the cosine is also positive in quadrant 4, so you have the cosine of 11 pi over 6 is square root of 3 over 2 also, but can't use that one because it's not in the right restricted area. So what do we have here? That the arc cosine of the square root of 3 over 2 is pi over 6, like that. The arc cosine, this will be the last one. I'm not going to spend too much more time on this. Let's say we have negative square root of 2 over 2. We're not sure what that is. Then we would say that the cosine of that answer has got to be negative square root of 2 over 2. We obey the restriction that the x value must be between 0 and pi for the restricted cosine function. So this has to be a quadrant 2 angle, and so this would be 3 pi over 4 right here. And so the cosine of 3 pi over 4 is negative square root of 2 over 2. And so the arc cosine of negative square root of 2 over 2 would be 3 pi over 4, like that. Okay, and so that's a real quick rundown of the arc cosine function and the restricted cosine function. We did exactly the same with the tangent. I'm not going to go through that as in much detail here. So we know that the tangent's not 1-to-1, so we restrict the domain. And in this case, we are looking at the domain to be just all the values from negative pi over 2 to pi over 2, open interval there, right? Because remember, the tangent function is not defined at negative pi over 2 or pi over 2. You have vertical asymptotes there. So that's the domain of the restricted tangent function. And then the range there, well, remember the range for the tangent is just all real. So that goes from negative infinity to infinity. So if we now look at the arctangent function, the inverse of that one, then its domain would be all reals, negative infinity to infinity, and its range would be the open interval from negative pi over 2 to pi over 2, like that. And like the sine function, you're just getting quadrant 1 and 4 angles when you're looking at that. All right, so that would be our tangent function. And then you have similar restrictions for, so similar restriction issues for arcsecant x, arccosecant x, and arccotangent x. For in the textbook, a nice little summary of all those restrictions can be found in your textbook. Oh, actually, I guess they can't be found in your textbook. I don't think. Well, they are. They're at the very front of the book. They're not in the calculus section. They're in section 1.4. So the restrictions are all in section 1.4, and very quickly those would be found on in your book on page 87 of your book. So the restrictions can be found on page 87. Okay, so now what we want to do is we want to look at calculus and the inverse trig functions. Okay, so here at the end here, we'll say now let's look at derivatives and inverse trig functions. All right, so what we're going to do is we're going to start off with f of x equal arcsine x. And we're going to go ahead and we're going to derive the derivative for this function. So now remember that this would be the same thing as y equals arcsine x. But don't know what the derivative of the arcsine function is. So what we do need to do is rewrite this statement in an equivalent way, so it's only using functions that we do know derivatives of. So we write the equivalent inverse statement, in this case that sine y is equal to x, because I do know the derivative of the sine function. Now the only thing that this does, or not the only thing, but the one thing that this does do is that it changes an explicit function into an implicit function. In other words, the first one's solve for y, the second one's not solve for y. That's okay. So what do we got to do here? We got to use implicit differentiation, which we talked about last week. So we use implicit differentiation to find the derivative here. So we differentiate both sides of that equation with respect to x. So this is what we're doing. And to kind of remind you, remember that when you're using implicit differentiation, you are assuming that y is some function of x. You just don't know what it is. And so when I take the derivative of the sine of y, I must use the chain rule. So the derivative of the sine function is the cosine function, so you have the cosine of y, times the derivative of the inside function, but the inside function in this case is just y, and so that would be dy dx, like that. The other side is easy. The derivative of x with respect to x is simply just 1. So we've differentiated both sides there with respect to x. So this is the implicit differentiation process. And then we solve for dy dx, and we get dy dx is equal to 1 over cosine y. All right, so now what does this mean here? How do we interpret 1 over the cosine of y? So the derivative of y with respect to x, first of all, would be 1 over cosine of y, but remember y is arc sine x from the very beginning of this problem. Right? Remember, we know that y is equal to arc sine x, so we're using that in that statement there. We are replacing y with arc sine x. Now this is the cosine of the arc sine of x, so this is not inverse cancellation right here. So what do we make of this statement here of cosine of arc sine of x? How might we rewrite that expression maybe in something that's something we could handle a little bit better? So what we're going to do here is we're going to use a little trick that's associated with a right triangle. We're going to use some right triangle trigonometry here. We are going to let theta be equal to arc sine x. Now remember that the arc sine function is restricted to just giving you values from negative pi over 2 to pi over 2. And so, you have to kind of keep that restriction in mind, but it turns out that for a problem like this, the restriction is not going to be too heavy of a burden for us. So if theta is arc sine x, then sine of theta would be equal to x. And then using a little right triangle here to picture that statement, in other words, using right triangle trigonometry, if that's the angle theta right there, we know that the sine of theta is opposite over hypotenuse, and so that would be x in 1 for my opposite side and my hypotenuse side. And then using the Pythagorean theorem, you would get the other side of that triangle to be the square root of 1 minus x squared. All right, so now, okay, so how is this going to help us? Well, cosine of arc sine of theta is arc sine of x is equal to theta, so this is really just cosine of theta, right? We just replace arc sine x with theta. And so if I take my picture right here, my right triangle picture, and I look at cosine of theta, cosine is defined to be adjacent over hypotenuse, and I get the square root of 1 minus x squared. So notice that the cosine of the arc sine of x has got the value of the square root of 1 minus x squared. And so what we've got here is that our little derivative formula that we just derived is really 1 over the square root of 1 minus x squared. So now notice this is kind of a really different from anything we've done before, in that throughout the course so far, if we've taken the derivative of an algebraic function, we got an algebraic function as the derivative. If we take the derivative of a trig function, we got a trig function as the derivative. But notice this is a case where you've got a trig function, the arc sine of x, and its derivative is an algebraic function. So that you have that if what we've just derived is that if f of x is arc sine x, then f prime of x, or dy dx, is equal to 1 over the square root of 1 minus x squared, right? And there's our derivative. All right, so that's our first property here. Now you'll see it written in other ways also. So let's see, if we use differential notation on the next page, and so using differential notation and the chain rule, let's extend this a little bit. So using differential notation and the chain rule, we have this statement that the derivative with respect to x of the arcsine of u of x, in other words, you're taking the derivative of the arcsine of some function of x, so combining, this is just using that rule that we just derived on the last page, and the chain rule, then this would be 1 over the square root of 1 minus u of x quantity squared times the derivative of u with respect to x, like that. That would be the derivative. Or if you were going to write this with prime notation, you could simply write this as u prime of x over the square root of 1 minus u of x squared. And frankly, this is probably the way most students remember it, is the second way, not with the differential notation, but the second way. That this is the derivative of u divided by the square root of 1 minus u squared. And there's our arcsine form right there. All right, so writing out the other derivatives, we have the derivative of arc cosine of u of x is a very similar expression. It's negative u prime of x over the square root of 1 minus u of x quantity squared, like that. The derivative of arc tangent, arc tangent of u of x would be equal to u prime of x over 1 plus u of x quantity squared. Notice there's no radical in this one, so it's a little bit simpler. The derivative of arc secant of u of x would be u prime of x divided by the absolute value of u of x times the square root of u of x squared minus 1. And that absolute value comes from the restrictions that come along with the arcsecant function. You have to guarantee that your answer has the correct SIGN associated with it. And then I'm just going to say and so on for the other trig functions. All these forms are in your book on page 307. Forms are in textbook on page 307. To be honest with you, these are the four that are going to be the most important for us: arcsine, arccosine, arctangent, arcsecant. In fact, arccosine we'll find is not even as important as arcsine for various reasons. You'll see that later in the semester. And these are the ones I'm going to tend to center on as we go through the semester. They're, in my opinion, the more important ones. Let's go ahead and look at the arctangent and derive the arctangent form, the basic arctangent form. So let's do that one also before we look at any more examples. So let's derive the derivative form for y equals arctan x. So notice not arctan of some complicated function, just arctan x here. All right, so we do similar process that we used with the arcsine. So we have tangent y is equal to x. And then we differentiate both sides of this statement with respect to x, just like we did with arcsine a couple of screens ago. Remember that this is implicit differentiation, and so you have to use the chain rule. So the derivative of the tangent of y, the derivative of tangent, that's the outside function, its derivative would be secant squared. And that'd be secant squared of y, and then times the derivative of the inside function, which would be dy dx. And that would be equal to 1. So then we have the derivative of y with respect to x is 1 over secant squared y. And we could maybe help ourselves a little bit by writing that as cosine squared y instead of 1 over secant squared. And then what's y equal to from the very beginning of the problem? Y is equal to arctan x. So the derivative of y with respect to x would be cosine squared of arctan x. All right, so this is a problem where we might use our right triangle trick to try to find an algebraic expression for this. So what we do is put a little box here. We're going to let theta equal arctan x. Right, so that means the tangent of theta is equal to x. And using our little right triangle scheme here, if this is theta, we know that tangent is defined to be opposite over adjacent, so this would be x and 1, and the hypotenuse then would become x squared plus 1, like that. And now what are we trying to do here? We're trying to find the cosine, right? You've got the cosine of the arctangent of x. Arctangent of x is equal to theta, so this is cosine squared of theta that we're trying to look at here. Arctan x was equal to theta. So cosine of theta is and I did. This should have been the square root of x squared plus 1 there for the hypotenuse. I wrote x squared plus 1, but it should be the square root of x squared plus 1. So cosine of theta from the picture is adjacent over hypotenuse to be 1 over the square root of x squared plus 1. And so cosine squared of theta, x squared plus 1 has got to be positive. So this would be okay to just write this as 1 over x squared plus 1. And so what do we have over here? The dy dx is cosine squared of theta, because that's what theta was, is arctangent. And so we get the dy dx is equal to 1 over x squared plus 1. And we've derived the basic form for the arctangent function. All right, so now for the rest of the lecture, what I want to do is just look at some examples of differentiation for inverse trig functions. All right, so first example, we have f of t is equal to arcsine of t squared. So start off with some relatively simple derivatives. So what do we have here? We have a form that we wrote down a few minutes ago that we derived, that the derivative of arcsine of u of x was equal to u prime over the square root of 1 minus u squared. Just kind of abbreviating things there a little bit. So in our problem, what's our u is going to be t squared, right? So f prime of t in our problem would be u prime, so that would be 2t over the square root of 1 minus u squared. And so that'd be 2t over the square root of 1 minus t to the fourth. And that would be our derivative function right there. Okay. Another example. So like I said, we're going to work through several examples here. F of x is arctangent of x cubed. Okay, so let's write down our rule. And I would definitely recommend you have these rules in front of you when you're working through these problems initially. Write them down over and over and over again is what I would do. The more you write them down, the easier it will be to remember these later. So remember, the derivative of the arctangent is u prime over 1 plus u squared. So in our problem, f prime of x, u in this case would be x cubed. So it'd be u prime, that'd be 3x squared over 1 plus x cubed squared. And so that would be 3x squared over 1 plus x to the 6th. And that would be our derivative function there. All right, doing very good here. So next problem, f of x is x arc cosine of x. All right, so with arc cosine of x, first thing is this is a multiplication problem, so you have to use the product rule. Please don't overlook all those basic rules for differentiation. So this is a product rule problem. Don't get in a hurry in a problem like this and just focus on the arc cosine. Look at the overall structure of the function that you've got as far as how you're going to calculate the derivative. So let's see. Let's not forget that what the rule is that we wrote down for the arc cosine, that the derivative or the arc cosine of u of x, we'll just say of u, is negative u prime over the square root of 1 minus u squared. All right, so our derivative, in this case, f prime of x, product rule would be the first factor times the derivative of the second factor. So the derivative of arc cosine of x would be negative 1 over the square root of 1 minus x squared. And then that would be plus the second factor times the derivative of the first, but the derivative of the first is just 1. So you said 1 times arc cosine x. All right, so f prime of x would be negative x over the square root of 1 minus x squared plus arc cosine x. Okay, so that shouldn't be too bad. All right, in your textbook, I'm on page 310 in your textbook. And so let's look at an example out of your textbook. So let's say we have, or look at problem number 284. So this is problem number 284. You have y equals inverse cosine of 2x times inverse sine of 2x. Now, I'll be honest with you, typically I wouldn't write it that way. I would typically use the arc notation. And so I would write it as arc cosine of 2x times arc sine of 2x. Remember, those are the exact same problem. It doesn't, you'll see it written kind of interchangeably as far as which way you're going to write it. So just, kind of point that out. All right, once again, this is going to be the product rule. Right, so the derivative there, y prime, would be the first function, arc cosine of 2x, times the derivative of arc sine. But the derivative of arc sine is negative u, or I'm sorry, is u prime. So u is 2x there. So u prime would be 2 over the square root of 1 minus u squared. So it would be 1 minus 2x quantity squared, like that. And then this would be plus the second factor times the derivative of the first factor. So the derivative of the first factor would be negative 2, because it would be negative u prime over the square root of 1 minus u squared. And that would be times arc sine of 2x, like that. And so y prime would be 2 arc cosine of 2x divided by the square root of 1 minus 4x squared minus 2 arc sine of 2x over the square root of 1 minus 4x squared. They have the same denominator, so you might as well go ahead and write it as one fraction. And this would be the square root of 1 minus 4x squared in the denominator, and in the numerator you'd have 2 arc cosine of 2x minus 2 arc sine of 2x, like that. And that would be our derivative. Kind of a little bit of a messy form, definitely. So, okay, next problem I want to look at. And this will probably be our last problem of the day. So let's say we have this equation, arctangent of xy equals arcsine of x plus y. So notice right away that this is in implicit form. And so you're probably using implicit differentiation here. The problem is find the, or write the equation of the tangent line at the point 0, 0. So what are we going to do here? We're going to find dy dx, or y prime, implicitly. So we take the derivative of both sides of this equation with respect to x. So the derivative of arctan of xy equals the derivative with respect to x of arcsine of x plus y. And definitely not trivial. So on the left side, it's an arctangent, and so the form is u prime over 1 plus u squared. And so this would be u prime over 1 plus u squared. The u prime part is the derivative of xy, so that's the product rule. U is xy there, so that'd be first times the derivative of the second plus the second times the derivative of the first, but the derivative of the first is just 1 with respect to x. So that'd be the product rule in the numerator. The denominator would just be 1 plus u squared, so it'd be 1 plus xy quantity squared. All right, and that would equal, on the other side of the equation, you have a fraction over there also. And on the top, this is going to be u prime, and on the bottom, it's going to be the square root of 1 minus u squared. That's our arcsine form. All right, so the derivative of x plus y with respect to x, that would just be the derivative of x, which is 1, plus the derivative of y, which is dy dx. And in the denominator, you'd have the square root of 1 minus u squared, so it'd be 1 minus x plus y squared. Now, if you recall, so that's your really, really messy expression right there. And if you recall that typically what we do is solve for dy dx, but there's not really any reason to solve for dy dx here. All we got to do is find dy dx when x and y are both 0, right? Because the point 0, 0. So here all you're doing is substituting 0 in every place you see an x or a y. And so that, I'm going to actually put this in a different color so it kind of stands out at the bottom here. You'd get 0 times dy dx plus 1 times dy dx, all divided by 1 plus 0 times 0 squared, like that, is equal to 1 plus dy dx over the square root of 1 minus 0 plus 0 squared. And so what that gives you, and I think I do have a slight mistake in there that I've just noticed. So I'm going to go back in. If you notice that in the derivative on the left side of the equation, I have a 1 plus dy dx, right? And that 1 shouldn't be there. That 1 should actually be a y right there. That should actually be a y. And so that should be a 0 down here when I evaluate it. And so that ends up giving you 0 on the left side of the equation. Yeah, I'm glad I noticed that. So you have 0 over 1 equals 1 plus dy dx over 1. And so you end up, when all said and done here, with dy dx being equal to -1. Now remember, what you're trying to do is find the equation of the tangent line. And so what we just found is that the slope of the tangent line is -1. So the slope of the tangent is -1. And so that allows us to write the equation of the tangent line. So the equation of the tangent line, go on to a new screen here. So the equation of the tangent line remember it's through 0, 0, would be given by y minus 0 equals -1 times x minus 0. In other words, y equals -x. That would be the equation of the tangent line through that point 0, 0. All right, so we started with this kind of complicated equation, arctan of xy equals arcsine of x plus y. We wanted to look at the equation of the tangent line at 0, 0. So we had to find dy dx implicitly, so we differentiated both sides of the equation. And when we differentiated both sides of the equation, we got this relationship right here. That fraction has got to equal this fraction right here. And I've got alongside of each of those fractions how they were calculated. Right, on the left side, it was u prime over 1 plus u squared. On the right side, it was u prime over the square root of 1 minus u squared, because the left side was an arc tangent, the right side was an arc sine. Now, when I got that form, and remember, when I originally wrote it, I made a slight mistake, and I put a 1 in the numerator there where there should have been a y. I circled that. You don't really need to solve for dy dx in this case, because not algebraically at least, just substitute x equals 0 and y equals 0. And when you do that, you get a pretty simple expression. You end up with just 0 equals 1 plus dy dx. And so you get dy dx has got to be -1 when x is 0 and y is 0. And then from there, we can write out the equation of the tangent line. Okay, so that's it. We're finished with talking about the inverse trig functions and derivatives. You need to be working on homework out of the textbook. Certainly that covers section 3.7. And so now in chapter 3, the only thing we haven't covered yet is section 3.9 on exponential and logarithm functions and their derivatives. So on Wednesday's class, we are going to talk about the functions f of x equals e to the x, and its inverse function, f of x equals natural log of x. And we're going to look at derivatives for these functions. So we'll have some work, a little bit of work to do. We'll do a little bit of reviewing about e to the x and natural log of x. And we'll also look at a little bit with other bases for logarithms and exponential functions. We're not going to spend a lot of time with that, but we will also look at not just base e, but base a exponential and logarithm functions a little bit. Not a lot with that, but a little bit. All right, so have a great rest of the afternoon or evening whenever you're watching this video. Don't forget my online office hours the rest of the week, 8 to 9 in the evening, Monday, Tuesday, Wednesday, and on Thursday from 1 to 2. Don't forget that I should have your exam grades posted on your D2L gradebook by the end of the week, by Thursday hopefully, and I will send you an email when I post those grades, and that you can get a copy of your graded exam by just emailing me, and I will respond to that email with an attachment that's your graded exam. So have a wonderful, wonderful day. Please, I'm begging you to continue to work on practice problems every day. You really need to practice calculus. You can't afford to wait until just before the exam or just before a homework assignment is due to cram a bunch of work in at the end. You've got to work on this consistently. I'm thinking about you as going into Cal 2 and in Cal 3, that it's just not going to work for you to put off the effort on these problems and practicing them until test time or homework is due time. Make your effort as consistent as possible. All right, have a great day.